The biggest black hole is a lie. The black hole lie. The biggest black hole ever discovered might not exist the way we think it does, and that's exactly what makes this story addictive. Every few years, another headline slams into your feed. Astronomers find record-breaking black hole. New cosmic heavyweight dethrones ton 618. It feels like a cosmic leaderboard, like the universe is keeping score. But here, the gut punch. Those record-breaking numbers do mean what we think they do. Because once gravity starts warping space and time, the whole idea of bigger collapses under its own weight. We love these cosmic leaderboards. It's wired into us. One moment it's ton 618 stealing the spotlight, an invisible engine hidden 10 billion light-years away, blazing brighter than 1,000 galaxies combined. Then, deep in the dark, something even more monstrous, like PhoenixA, waits quietly, swallowing suns without a whisper. The headlines call them rivals. But here's the thing. Can you actually compare objects that literally twist the definition of object itself? That question hooks you before you even realize how strange the truth gets. That's the real problem. When you step close enough to a black hole, the rules of scale, distance, and even time bend so completely that normal measurements lose all sense. What we call biggest, out here on Earth, collapses into nonsense next to a gravitational singularity that defines its own meaning of reality. And here's where your brain starts to bend with it. The deeper question, the one this story unravels, isn't which black hole tops the list. It's why the list itself might be a cosmic illusion. Because in a universe where even the measuring tape stretches and curves, what does size even mean anymore? Stick with me. By the end, you'll see why the biggest black hole might be something the universe refuses to let exist at all. And how somewhere beyond our reach there could be black holes so vast, they don't just break our rules, they erase them. The obsession with the biggest. Why do we even care about what's biggest in the first place? From the tallest mountain to the fastest car, from Olympic records to endless lists ranking galaxies and stars, our minds are wired to compare. It gives chaos a sense of order, a feeling that we understand our place. But when we carry that same instinct into astrophysics, something beautiful and strange happens. Nature refuses to play along. Astronomy headlines feed this obsession perfectly. They boil unimaginable cosmic complexity down to one clean, clickable number, the largest black hole ever found. But that one phrase hides layers of uncertainty, debate, and incomplete physics behind it. In a field where almost everything is inferred, not directly measured, those records rely on fragile definitions. What you call the biggest black hole depends entirely on how you decide to define big. Take the idea of black holes themselves. We talk about them like they're gigantic spheres floating in space, solid spheres with edges, diameters, borders. But that mental image is a misunderstanding born from the way we experience size here on Earth. In truth, a black hole doesn't even have a surface. It's just a region of spacetime where gravity becomes so strong that beyond a certain boundary, the event horizon, not even light can escape. There's nothing solid to measure. What we call its radius is really a kind of mathematical construct, a point where the equations say this far and no further. But simple stories sell better, so the nuance gets stripped away. Scientists spend years refining models to estimate a supermassive black hole's mass based on how nearby gas moves or how its galaxy glows. Then an article comes out framing it like a trophy match. PhoenixA beats ton 618 by 10 billion solar masses. It's irresistible. Yet in reality, those masses rest on assumptions so different that comparing them is like ranking the loudness of a painting against the color of a song. Think about it, what even counts as bigger for something that bends spacetime? Mass seems straightforward enough until relativity complicates it. A more massive black hole has a larger gravitational reach, but the space it occupies isn't truly bigger, because inside, location and size stop working the way we expect. Diameter. The event horizon grows with mass, but if you measure it visually, gravitational lensing makes it appear even larger depending on where you observe from. Influence. Every black hole's gravity stretches to infinity in theory, so where do you draw the boundary? This confusion mirrors something deeply human. Our need to measure everything, to assign rank, comes from how our brains evolved to survive in small, predictable environments. On a cosmic scale, though, those instincts mislead us. We crave hierarchy where none exists. The universe doesn't hand out trophies, it just evolves structures according to physics. But when we treat discoveries like a competition, we start missing the underlying story. Each black hole tells us something different about how the universe hides its most extreme transformations. Take TON 618 again. Discovered decades ago during radio surveys, it's so far away that the light reaching us started its journey when life on Earth was just beginning to crawl. We only know it exists by the way matter around it blazes as it falls inward, a quasar so brilliant it drowns its host galaxy. That brightness lets astronomers estimate its central mass, but also misleads them if they assume its accretion behaves like nearby ones. On the other hand, PhoenixA sits in a galaxy cluster whose gas releases torrents of X-rays, evidence of a black hole releasing energy into its environment, an entirely different measurement path. One blaze of light, one silence of heat, and both yield record masses. No wonder they contradict. Media rarely mention that these numbers carry large error bars, sometimes so large they overlap. The supposed gap between 67 billion solar masses and 100 billion solar masses might vanish once uncertainties are accounted for. It's not a leaderboard, it's overlapping fog. But fog doesn't make for good headlines, so the nuance disappears again. And still, we keep chasing that superlative. There's something emotional about it too, a reflection of how we look for boundaries in infinity. Saying this is the biggest ever feels like control, as if we've mapped the edge of the unknown. But black holes, by definition, are the unknown, regions cut off from the normal flow of cause and effect. The very thing that defines them invalidates our everyday logic. If we pull back, this obsession teaches us more about ourselves than about the universe. It shows how much we need clean narratives, how badly we want simple categories even in domains that thrive on paradox. Scientists know this tension well. They must communicate profound, abstract ideas to the public, balancing accuracy with accessibility. But the public's hunger for the largest, or the first, keeps bending these ideas back into record book form. Here's where it gets fascinating. The deeper researchers dive into the physics, the less biggest means anything at all. Relativity rewrites geometry. One observer's measurement of length or time can differ completely from another's in stronger gravity. So when we crown one black hole the champion based on apparent mass or radius, we're declaring victory over a game that spacetime itself doesn't allow us to play. That paradox, that blend of scientific humility and human ego, is what drives the whole question behind this story. In a sense, every biggest black hole we find is just a mirror held up to our curiosity. We project scale onto phenomena that transcend scale. And that's the real lie. Not that scientists exaggerate, but that our language can even describe something that erases the meaning of description. Before we can crown a cosmic champion, before we can even talk about which one wins, we first have to decide what bigger means in a universe where even distance depends on who's watching. Only then will we see why our entire notion of comparison falls apart under its own gravity, and why the next section dives straight into that mystery. What does size really mean when spacetime itself decides to bend the ruler we're using? What defines a black hole's size? At first glance, you'd think measuring a black hole would be simple. Find its center, draw a line to the edge, and there's your size. But the second you cross into the realm of extreme gravity, geometry stops behaving the way it does everywhere else. Even defining an edge becomes tricky because there isn't one, at least not in the solid, surface-like sense we're used to. What we call the boundary of a black hole is really a zone of no return, known as the event horizon, the invisible border where gravity's pull matches the speed of light. Beyond it, All paths lead inward. That's the first hint that a black hole's size is not about what it contains, but about where freedom itself disappears. Physicists formalize this using something called the Schwarzschild radius, a term that sounds technical but describes one simple relationship. The more massive an object, the larger the radius where light can no longer escape. In mathematical form, it scales directly with mass. Double the mass, double the radius. But while that looks clean on paper, spacetime curvature wrecks any sense of proportion we rely on in normal environments. Doubling the radius doesn't mean doubling the physical volume, because space itself is curved around the black hole like fabric pulled toward a bottomless drain. What appears from afar as expansion is, locally, distortion. And that's if the black hole is perfectly still and uncharged. The simplest version, the Schwarzschild solution, assumes no spin, no electric charge, just mass sitting in infinite emptiness. But real black holes spin rapidly and may hold some charge. When spin enters the picture, we get a Kerr black hole, and suddenly the geometry reshapes again. Rotation flattens the event horizon slightly, drags space around it through a process called frame dragging, and creates an additional region outside the main horizon, the ergosphere, where nothing can remain still. Even defining a radius becomes ambiguous because the horizon's distance depends on your direction from the spin axis. Add charge as well and you move to the Reissner, Nordstrom model with dual horizons, an outer and an inner one. That complexity might sound mathematical, but it matters physically. Spin or charge changes how large the event horizon appears and how energy can escape. When astronomers talk about the size of black holes, they usually refer to the distance to that outer horizon. Yet that measurement evolves with the hole's properties, so no two definitions line up neatly. The most intuitive image comes from thinking about escape velocity, the speed needed to break free from gravity. On Earth, it's about 11 kilometers per second. At a black hole's event horizon, it equals the speed of light, nearly 300,000 kilometers per second. The surface where that equality holds defines what gets trapped and what escapes. But that surface isn't static. Imagine watching an object fall in. From your distant perspective, it slows down endlessly, never quite crossing the line. To the object itself, it plunges through in a flash. That time discrepancy, predicted exactly by Einstein's general relativity, means the location of the horizon can appear frozen or shifting depending on who's looking. So when scientists quote numbers like ton 618 radius is about 200 billion kilometers, that's a description relative to our viewpoint, not an absolute edge carved into spacetime. To a nearby observer, the geometry of that region could look radically smaller or stretched, because near the event horizon, even measuring rods and clocks distort. 1 second for us might be centuries there. A kilometer near the horizon doesn't represent the same intrinsic distance as a kilometer in open space. Every ruler bends under gravity. This leads to the next complication. How do we map something whose very presence changes the map? Astronomers get creative. They use indirect clues, radiation from orbiting gas, light bending around the hole, or the orbital speed of nearby stars to calculate an equivalent mass. Then they compute the radius theoretically. The size isn't observed, it's inferred. When the Event Horizon Telescope captured M87*''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''''', that wasn't an image of the black hole itself. It was the shadow, light distorted around the event horizon silhouette, roughly 2.5 times wider than the actual horizon. The real boundary lies hidden within, eternally invisible. This subtlety means that when you see diagrams comparing black holes side by side, like Jupiter compared to ton 618, they're useful approximations, not literal scales. The light travel time across ton 618 shadow might be weeks, but that's an abstraction for visualizing an object whose presence warps distance itself. If you could somehow stand near it, the concept of a cross wouldn't behave logically. Every direction would lead inward. Space stops folding outward, the way Euclidean geometry demands. You might wonder then, if we can't define a tangible boundary, why use radius at all? Because physics, even in curved space, still honors relationships. The Schwarzschild radius tells us something concrete about how mass interacts with light and time, even if it's not a physical surface. It's a marker in the equations where cause and effect relationships vanish over the edge. In black hole physics, that's the real significance, the point where external influence ends. And yet all of this scaling falls apart when compared across multiple black holes. One rotating rapidly might have an oblate horizon larger in one direction. Another might be distorted by surrounding matter. And a third, like TON 618, lies so far away that cosmic expansion itself stretches the light we use to calculate its mass. That redshift alters our inference of both its brightness and size. Even the concept of mass becomes tricky. Gravitational mass, inertial mass, and observed mass diverge when spacetime curvature gets extreme. At cosmic scales, the geometry itself participates in the measurement. Rearranging those variables can give you slightly different sizes for the same black hole. That's why TON 618 reported size sometimes differs by billions of kilometers depending on the study. Each value reflects a different method: spectral line width, thermal emission modeling, or quasar luminosity correlation, all pointing to the same reality. We're seeing how the black hole affects its environment, not the black hole proper. When you stitch all these ideas together, you realize that size is shorthand for a web of interdependent conditions. It's not just a radius, it's a relationship between gravity, light, and time. Every factor tweaks what astronomers can deduce. And because relativity couples those dimensions inseparably, measurements from distant perspectives are literally flattened through differing time frames. The farther you look, the more those distortions multiply. So, defining a black hole's size might sound like an act of measurement, but in truth, it's an act of interpretation. What we call big becomes a projection of our models, shaped by assumptions about physics that might not even apply near an event horizon. The next logical question, then, isn't what the radius equals. It's how we can test those interpretations when direct observation is impossible. So if the boundary itself bends and the apparent horizon shifts depending on who's watching, how do astronomers measure one at all? That's where the next part of our journey begins. Learning how science turns the unseeable into numbers using the pure geometry of motion and the faint glow of matter on the edge of oblivion. Measuring the unmeasurable. So if we can't point to a definite boundary or photograph the surface, how do astronomers measure something that refuses to be seen? The answer is that they don't measure the black hole itself, they measure its influence. Every estimate, every claimed mass, every record-breaking headline comes from studying the motion of the things trapped in its gravitational grip. When light can't escape, motion becomes the language that reveals what hides inside. For nearby black holes, that usually means tracking how stars or gas clouds orbit around the invisible center. The technique feels like cosmic detective work. You take repeated observations, record the orbital period, and then apply Kepler's laws, the same rules that describe planets revolving around the sun. The faster those objects whip around, the more mass must be pulling on them from within. Multiply the velocities, map the distances, and you can infer a central mass down to striking precision. It works beautifully for supermassive black holes in galaxies within a few 100 million light-years of us, objects like Sagittarius A in our own Milky Way or M87* in Virgo. There, individual stars and gas features can be tracked frame by frame. But that trick collapses for the distant monsters like TON 618. 10 billion light-years away, we can't separate individual stars or orbits. All we see is a blinding quasar, the light of a superheated accretion disk spinning close to the speed of light. In that swirl, gas is racing around the black hole, shining across the spectrum from X-rays to visible light. Its brightness and flicker encode clues about the black hole's mass. Astronomers look at specific spectral lines, narrow fingerprints produced by elements like hydrogen or carbon. These lines get broadened by the Doppler effect. Gas moving toward us shifts the light bluer, gas moving away pushes it redder. The broader the line, the faster the motion, and the heavier the object driving it. That's how TON 618 breathtaking estimate, around 60 billion solar masses, first emerged. Researchers in the 198s analyzed its ultraviolet spectrum and found carbon lines enormously stretched, corresponding to orbital speeds of thousands of kilometers per second. Apply the right scaling model, and you get a remarkable number. But that number depends on assumptions about the geometry of the gas disk and how efficiently the black hole is feeding. Change those parameters slightly, and the result can shift by tens of billions of solar masses. It's less a single measurement and more a probability cloud shaped by our model of the system. Another layer of data comes from gravitational redshift. Light climbing out of a deep gravitational well loses energy, stretching toward longer wavelengths. By analyzing how those spectral lines are displaced, astronomers can back-calculate the strength of the gravitational field. For nearby systems like the compact binary used to infer Cygnus X1's mass, these effects are measurable. For faraway quasars, they're swamped by cosmic expansion. That's why uncertainties balloon for objects like TON 618. The night sky itself is expanding between us and the source. To overcome those limits, radio astronomy steps in. The Event Horizon Telescope, the network that linked dishes across the Earth to capture the first image of M87*, doesn't photograph the black hole. It maps how radio waves scatter and interfere after bending around the event horizon, forming a dark central shadow. The radius of that shadow, compared to models produced by general relativity, gives the mass indirectly. For M87*, it matched predictions beautifully, confirming that Einstein's equations hold even at such extremes. But when we try to apply the same technique to distant quasars, the signal becomes too faint, too smeared by intergalactic dust. At that scale, the universe removes most of our direct evidence and leaves us to work through inference alone. Every tool in this toolkit, orbital dynamics, redshift, imaging shadows, comes with its own translation errors. Distance measurements can be biased by how cosmic expansion twists space between galaxies. Brightness estimates rely on knowing how much light is absorbed or scattered along the way. Even the shape of an accretion disk can fool our models. Tilt it differently, and you'll overestimate speed or mass. Uncertainty isn't a flaw in these techniques, it's baked into them. The farther you look, the more you're measuring the cosmos folded through time. That's why mass estimates for giant candidates vary so wildly. Take PhoenixA. It sits about 5-7 billion light-years away in the heart of the Phoenix cluster. Astronomers can't observe its disk directly, so they rely on feedback models, studying the immense X-ray glow produced as the black hole heats surrounding cluster gas. By comparing how much energy is being pumped into that gas versus how quickly it cools and condenses toward the center, they infer the engine's power, and from that, its mass. Some analyses yield a modest 12 billion solar mass core. Others push that number up toward 100 billion. Different modeling assumptions, same data. Scientific humility compels researchers to admit both could be right until better evidence arrives. Closer examples reveal why even tiny changes matter. In the Milky Way, when astronomers refined the distance to Sagittarius A by just a few percent, its calculated mass shifted by nearly 500,000 suns. Now scale that problem up over billions of light years, where light curves through expanding space and galaxies evolve across epochs, and you start to see why ranking black holes feels absurd. We're comparing guesses, not objects. And yet these guesses remain remarkably powerful. They let astrophysicists test ideas of black hole growth, energy output, and the physics of accretion that can't be reproduced in labs. Each observation constrains the range of possible masses, gradually sculpting a clearer picture from noise. When multiple independent methods, say disk modeling, variability timescales, and emission line widths, all converge on similar results, confidence climbs. That's why, despite the caveats, we can still say TON 618 and PhoenixA belong among the universe's most massive known gravitational wells. The fascinating twist is that each technique in trying to define the unseeable reveals more about our cosmic perspective than about the black hole itself. We measure light delay, orbital motion, or radiation strength, and each measure passes through layers of interpretation tied to our position in time and space. The black hole, meanwhile, remains silent, unchanged by our efforts to label it. It doesn't have a mass in the human sense. It curves spacetime according to its energy content. What observers on Earth perceive as billions of solar masses is really just the mathematical translation of how much curvature is required to produce the dynamics we see. All of this leads to a deeper philosophical tension. Measuring a black hole isn't about defining an object, it's about reading its consequences. We witness the ripples in surrounding matter and light, and from those disturbances reconstruct a phantom portrait. The clearer that portrait appears, the more we must remind ourselves we've never actually seen the thing casting the shadow. Our numbers describe its impact, not its reality. And that's the irony behind every new headline trumpeting largest black hole discovered. Each new record arrives born on uncertainties so vast that the next observation could overturn it entirely. In practice, the crown of biggest passes between candidates not because they're growing, but because our measurement techniques keep evolving. As instruments sharpen, as models improve, our understanding shifts. What we call discovery is often revision. In a universe that expands faster than our comprehension, even the most precise observation is provisional, a snapshot filtered through space, time, and imagination. The black hole's scale becomes a mirror for the limits of our perception. And so the bigger question remains open. If our best science can only outline their effects, what other giants might exist beyond any measurable boundary, waiting where no data can reach? Speaking of giants, one black hole turned this entire conversation into legend. Its light has traveled for billions of years, crossing half the observable universe to reach our telescopes, and it became the symbol of everything we think we know about cosmic magnitude. That's where we're heading next, the extraordinary story of TON 618, the quasar that defined what impossible size really looks like. The case of TON 618. TON 618 isn't just another entry on a cosmic leaderboard. It's the black hole that turned the idea of record-breaking into a paradox. Every time its name appears in scientific papers or headlines, it carries an almost mythical weight. 60 billion suns packed into a gravitational well so powerful that light itself stretches and fades trying to escape its glare. But what's fascinating isn't just how massive TON 618 might be. It's how uncertain that number truly is, and what its very discovery reveals about the limits of cosmic measurement. The story starts in the late 196s, when astronomers were still puzzling over mysterious radio sources that didn't match any known stars. At an observatory in Bologna, radio surveys aimed at mapping the northern sky picked up an unusually strong signal. When cross-checked with optical plates from the Tonantzintla Observatory in Mexico, the same source appeared as a bright, blue-tinged point. It looked like a star at first, hence the TON in its name, but its spectrum held the giveaway clue. Deep ultraviolet emission lines shifted far toward the red end of the scale. That redshift meant it wasn't a nearby star at all, but a quasar, an active galactic nucleus powered by something extraordinary at its center. By the early 198s, astronomers were refining spectroscopy techniques to analyze these quasars in detail. When they looked at TON 618 light, they found that its spectral lines were broadened almost beyond recognition. The gas racing through its accretion disk wasn't moving at mere thousands, but tens of thousands of kilometers per second. Feeding those velocities into dynamical models yielded an astonishing inference. The object driving this disk had a mass of roughly 40 to 60 billion suns. That single result catapulted Ton 618 from obscurity into superstardom. A glowing beacon declared the heavyweight champion of the cosmos. But those early calculations came with caveats. They assumed that the gas orbiting Ton 618 followed the same geometry as the accretion disks we see around closer quasars. In reality, no one could confirm that. A small difference in the disk's inclination could double or halve the estimated velocity spread, swinging the derived mass by tens of billions of solar masses. Adding to the uncertainty, the quasar's brightness depends on how efficiently matter converts to radiation as it falls inward. Change that efficiency factor, and the mass result changes again. Ton 618 became legendary not only for its supposed size, but for how fragile that estimation was. Zoom out to its cosmic address, and the picture becomes even stranger. The light we collect from Ton 618 began its journey more than 10 billion years ago, when the universe was less than a quarter of its current age. That means we're observing it as it looked during an era when galaxies were still assembling. Yet somehow, by that young cosmic age, Ton 618 black hole had already reached tens of billions of solar masses. Under standard models of black hole growth, even feeding continuously at the Eddington limit, there simply isn't enough time to reach that mass from any plausible seed. So either our physics is missing a shortcut, or our measurement is stretching the truth. Astronomers started exploring both possibilities. Some proposed direct collapse models, where enormous primordial gas clouds bypassed the normal star phase and imploded straight into black holes hundreds of thousands of times the sun's mass. Others suggested continual super-Eddington feeding, accretion rates so high that radiation pressure failed to blow surrounding gas away. Both ideas remain controversial, partly because they push against well-tested principles of radiation balance. But Ton 618 implied growth demands something extraordinary, so theorists keep those doors open. Meanwhile, observational astronomers have revisited Ton 618 again and again with upgraded instruments. Each time, they refine how they split its light, subtract background noise, and simulate the quasar's intricate structure. The revised numbers bounce between 40 and 66 billion solar masses. Some studies even lower it to about 35. That spread may sound drastic, but it highlights how much interpretation sits behind each figure. We can't weigh a black hole on a scale. We can only back out its mass from the curvature it imprints on surrounding matter and light. Despite the uncertainty, Ton 618 retains a practical use. It shows the upper boundary of what our current models can reasonably support. If its true mass lies near the high end of estimates, then even the most optimistic growth theories strain to explain it. If it's lower, it still exemplifies how bright a quasar can burn when fueled by a powerhouse core. Either way, Ton 618 pushes astrophysics to its conceptual limits. Let's step inside, at least in imagination. Its event horizon would stretch across about 200 billion kilometers, roughly 40 times the size of our entire solar system. A photon, traveling at light speed, would take weeks to cross its diameter. Around that horizon spins an accretion disk so energetic that it outshines entire clusters of galaxies. In visible light, it wouldn't appear black at all but blinding white-blue, with jets of plasma erupting along its poles and vanishing into intergalactic space. None of that light comes from inside the horizon. It's the collateral glow of matter losing its last fight against gravity. If you could somehow watch Ton 618 up close, you'd witness optical illusions unlike anywhere else. The extreme curvature would warp background stars into rings and arcs, wrapping the universe around its silhouette. Time would crawl near its edge. To a distant observer, infalling matter would seem to freeze as it approached the horizon, but to the matter itself, the plunge would last only moments. Every physical concept, distance, duration, brightness, loses its ordinary meaning. That's why calling it the largest black hole almost misses the point. Its very existence distorts what scale means. In the scientific community, TON 618 has also become a case study in communication. The media love its superlatives because they sound definitive. The biggest black hole ever found. Yet astrophysicists who work on it emphasize that they're comparing models from inconsistent datasets. The uncertainties can reach a factor of 3, effectively erasing any clear ranking with rivals like PhoenixA or S50014 plus 81. In internal discussions, researchers treat those titans as belonging to the same ambiguous class, ultramassive black holes, rather than competitors. Beyond about 20 billion solar masses, every estimate sits on theoretical quicksand. Still, there's value in chasing the extremes. By pushing measurements to the edge, scientists expose the cracks in existing theory. TON 618 tells us that our understanding of black hole formation may be incomplete, that accretion physics might change under conditions we can't replicate nearby. Even if its exact mass someday proves smaller, the lesson remains that nature doesn't recognize our conceptual ceilings. There's also a psychological dimension to TON 618 fame. It acts as a mirror for our fascination with limits, the same impulse that drives mountaineers to tallest peaks or engineers to fastest speeds. Headlines about the biggest black hole satisfy a primal need for boundaries, but TON 618 paradox is that it erases them. The more we study it, the less sure we are of where those boundaries lie. It embodies the scientific truth that progress often begins where certainty ends. Recent attempts to re-evaluate its luminosity using improved distance calibrations have actually trimmed its reputed mass slightly, yet its mystique survives untouched. Whether 40 billion or 60, it remains a beacon from the universe's adolescence, screaming across cosmic history to remind us how young the cosmos was when such monsters already roamed. Through its light, we glimpse both the power of physics and the weakness of our metaphors. And so TON 618 endures not as a crown on a cosmic hierarchy, but as a question mark carved in light. It forces us to confront the gap between what we can deduce and what the universe really is. If a single object can appear to break growth limits, distort time, and challenge every definition of size, maybe the throne of largest black hole was never meant to be claimed at all. Because hidden closer to home, another contender waits, not blazing like a quasar but humming beneath the X-ray glow of a galaxy cluster. While TON 618 shouts across time, this other giant whispers through heat and silence. It's called PhoenixA, and its quiet enormity may prove that the universe's true heavyweights don't always announce themselves with light. PhoenixA, the quieter monster. While TON 618 dazzles across the universe like a cosmic lighthouse, PhoenixA hides in near silence. No flamboyant quasar glare, no blinding jet slicing through visible light, just a steady, massive presence deep inside the Phoenix cluster, roughly 5-7 billion light-years away. Here, in a realm crowded with thousands of galaxies and suffused with hot X-ray emitting gas, this hidden black hole exerts influence on a scale that makes even TON 618 seem theatrical. It doesn't announce itself with brightness. It reveals itself through what it prevents, the cooling of an entire cluster's atmosphere. Astronomers discovered the Phoenix cluster in 2012 through NASA's Chandra X-ray Observatory, which detected a colossal concentration of superheated plasma radiating intensely in X-rays. Normally, that gas should cool, condense, and ignite vigorous star formation near the core. But something was rewiring the process. Streams of energy, jets invisible in optical light but bright in radio wavelengths, were blasting outward from the center, reheating the gas and throttling the cooling flow. The only phenomenon that could generate such power was a supermassive black hole devouring matter and converting gravitational energy into radiation. That central engine became known as PhoenixA. Estimating its mass, however, wasn't straightforward. Unlike TON 618, whose quasar light could be analyzed spectroscopically, PhoenixA's black hole is shrouded by the very cluster it dominates. To weigh it, researchers turned to indirect modeling. They compared the X-ray luminosity of the cluster's central region to the rate at which gas appeared to cool. The idea is simple in principle. If the black hole supplies enough energy to counterbalance that cooling, the required output reveals how heavy it must be. When translated into numbers, those calculations yielded staggering possibilities, from about 12 billion up to perhaps 100 billion solar masses. Ever since, PhoenixA has floated near the upper theoretical limit of what nature might allow. This wild uncertainty stems from the method itself. The X-ray data tell us how brightly the gas shines, but converting that glow into mass depends on assumptions about efficiency, geometry, and the black hole's feeding pattern. Some models treat the outbursts as steady over millions of years. Others see them as short, violent flares. Each scenario changes the deduced energy budget, and therefore the mass. In some fits, PhoenixA eclipses TON 618 by a comfortable margin. In others, it slips below it. The truth could lie anywhere between, and that range speaks volumes about what measurement really means. What makes PhoenixA fascinating isn't only its possible weight, but its temperament. TON 618 is the showman of the cosmos, a quasar shouting its existence through cosmic dawn. PhoenixA is the strategist, regulating entire galactic ecosystems. By releasing energy into its surrounding cluster, it prevents the rapid formation of new stars that would otherwise fill the central galaxy with blue light. Instead, it maintains a fragile thermal balance across hundreds of thousands of light years. This feedback loop defines one of the great puzzles in astrophysics: how black holes, tiny relative to their host systems, can dictate the growth and evolution of entire clusters. To visualize PhoenixA's power, consider this. Each of its jet outbursts injects enough energy to equal the total luminosity of the Milky Way spread over hundreds of millions of years. That output isn't continuous. It pulses as accretion waxes and wanes. The result is a set of vast cavities, literal bubbles carved in the surrounding plasma, visible in both radio and X-ray images. Those cavities trace the history of the black hole's influence, expanding like shockwaves through the cluster. From them, researchers can infer how much work the jets have done against the environment, offering yet another indirect handle on the black hole's mass. When the numbers are summed, they again point toward an engine tens of billions of suns deep. What makes this case so revealing is the silence surrounding it. PhoenixA doesn't outshine everything around it. It shapes everything around it. In astrophysical terms, that difference represents two regimes of accretion. TON 618 is radiatively efficient. Most of the matter falling in is converted into light. PhoenixA seems to operate in a mechanical or radio mode, ejecting energy mostly through jets rather than radiation. The irony is that the quieter mode may mask the heavier black hole. The stronger the jets, the less light escapes for distant telescopes to interpret, leaving us to reconstruct the monster by absence rather than presence. When scientists run cluster cooling simulations without such a powerful central object, the modeled galaxies form too many stars too quickly, contradicting observations. Insert a black hole of roughly 100 billion solar masses releasing episodic jets, and the numbers line up beautifully. It's a striking reminder that our sense of proportion in the universe depends on which kind of signal we notice. Sometimes the loudest entities are not the largest. Sometimes the giants speak in heat rather than light. The Phoenix cluster's environment also adds layers of complexity. Its intracluster medium teams with magnetic fields, turbulence, and merging substructures that all influence how energy moves outward from the core. Those interactions blur any clean distinction between the black hole's mass and its influence. A small adjustment to the assumed density of ambient gas can multiply or divide the inferred mass accordingly. Under such conditions, calling PhoenixA definitively the biggest borders on guesswork. Yet its existence proves something deeper, that black holes aren't isolated points but participants in cosmic ecosystems. Let's step back and compare styles. TON 618 sits alone in deep time, a relic from the early universe where matter flowed freely and galaxies were primitive. PhoenixA lives in a mature cosmos, enwrapped by a massive cluster assembled over billions of years. The two embody different chapters of cosmic evolution, one displaying youthful hunger, the other long-term control. Judging which is larger misunderstands the point. They're incomparable precisely because they sculpt reality on different scales. TON 618 across light years of individual brilliance, PhoenixA across megaparsecs of collective gravity. There's also an observational irony here. PhoenixA's host galaxy could house thousands of Milky Ways, yet to most telescopes it barely registers as distinctive. Its light is diluted by the cluster's glare. Without deep X-ray and radio surveys, we'd never suspect such a monster at its heart. That teaches an uncomfortable lesson. The brightest sources aren't always the most massive ones. For every blazing quasar we detect, there may be dozens of quiescent ultramassive black holes cloaked in cooler gas, their presence announced only through how they sculpt their surroundings. These quiet giants challenge our language. They don't conform to notions of object and size. Instead, they blur into their environments until the boundary between singularity and galaxy dissolves. Calling PhoenixA a black hole, singular, underplays that entanglement. It's more accurate to say it's a spacetime region coordinating the behavior of an entire cluster. That sounds poetic, but it's literal physics. Gravity couples everything within its domain so intimately that separating whole from host becomes artificial. And that brings us neatly back to the theme of this journey. If both TON 618 and PhoenixA depend on vast chains of assumptions, if both exist to us only as reconstructions from distorted light and gas, then maybe the real story isn't which one wins the size contest. Maybe the mystery lies in how spacetime itself conspires to hide the truth from our measurements. PhoenixA reminds us that silence can be as deceptive as brilliance, that absence of evidence isn't evidence of smallness, and that reality at these scales mocks our craving for comparison. Because here's the twist. For all its quiet, PhoenixA may represent a fundamental limit in nature's design. Its theorized 100 billion solar mass threshold sits near the regime where a black hole's own radiation or jets disrupt further infall. If that limit holds, PhoenixA sits on the precipice of physical possibility. Beyond it, normal equations of accretion break down, hinting that the universe might impose self-regulating boundaries on growth. Just as biological systems stabilize after reaching maturity, cosmic structures might cap themselves through feedback, gravity and energy locking into equilibrium. But even that elegant balance collapses once relativity enters. Near such immense gravitational curvature, the very scales we rely on, distance, mass, luminosity, mutate with perspective. The farther we stand, the more they stretch. The closer we imagine, the more they compress. And so, whatever PhoenixA truly is, record breaker, boundary case, or something outside those categories entirely, it exposes the flaw in our reasoning. We keep treating black holes like contestants instead of conditions of the universe. If both of these titans are guesses drawn from shadows, then perhaps the real giant lurking behind them isn't a single black hole at all, but the physics that refuses to yield a simple measurement. And that realization sets the stage for the next step in our exploration. Because after uncovering how these monsters defy definition, the looming question becomes unavoidable. What happens to our notion of scale itself when space and time, the very fabric we measure with, begin to bend? The core problem, space, time, and scale. At this point, the puzzle stops being about measurement and starts being about meaning. Because underneath all the arguments over which black hole is heavier or wider hides a deeper contradiction. The scales we use to rank them, mass, distance, size, all depend on space and time behaving normally. But around a black hole, space and time are anything but normal. Once gravity bends them far enough, every comparison we try to make turns paradoxical. Einstein's theory of general relativity tells us that mass doesn't just sit within space, it shapes space. Wherever there's energy or matter, spacetime itself curves, changing how nearby light and particles move. Around ultramassive black holes, that curvature is so severe that even the metric, the mathematical way we define distances, changes. What looks to one observer like a vast expanse could shrink to almost nothing for another. And since time is woven into the same fabric, clocks slow down too. Near the event horizon, seconds stretch into centuries relative to the outside world. So which frame of reference defines true size if everyone's rulers and clocks disagree? Imagine two observers. One orbits close to PhoenixA's horizon, the other watches safely from billions of kilometers away. The local observer measures a certain circumference around the black hole using light signals and timing pulses. The distant observer performs the same calculation from afar. Both are right within their own coordinate systems, but their results won't match. Spacetime curvature ensures that each measurement describes a different geometry of reality. The closer observer experiences compressed distances and dilated time, while the faraway one sees space stretched and time accelerated. The very fabric that connects their observations warps the meaning of size between them. This breakdown becomes dramatic through gravitational lensing. When light from background galaxies passes near a massive object, its path bends along the curvature of spacetime. Observers see the background distorted into arcs or halos, magnifying regions that might be billions of light years apart. Around something like TON 618, lensing isn't a subtle tweak, it's the dominant feature. Photons skim the edge of the horizon and loop around it multiple times before escaping. To an external telescope, that creates a shadow larger than the event horizon itself. The black hole appears much bigger than its actual radius because the light around it has been forced to take a longer route. We measure the detour, not the object. Time joins the illusion. Close to these giants, seconds and meters intertwine. Signals moving outward lose energy. Clocks slow so severely that from our perspective they nearly stop at the horizon. If you could hover safely nearby, a thought experiment only, your sense of time would feel normal, but looking outward to distant space you'd see the future unfolding at hyperspeed. From that same future's frame, your image would linger, frozen at the edge. Every event becomes relative, every interval elastic. Physical scale loses the constancy it enjoys under weaker gravity. Relativists describe this using metrics, the mathematical skeletons of spacetime geometry. For a simple, non-spinning black hole, the Schwarzschild metric defines how distances and durations relate near the mass. As you approach the singularity, coefficients in that equation approach infinity, meaning that our standard definitions of size or time no longer apply. Add rotation, as in the Kerr metric, and you get off diagonal terms, space dragging around with time, twisting the axes themselves. When coordinates twist, comparing two black holes becomes like comparing maps drawn on rubber sheets stretched in different directions. The data might be precise locally, yet meaningless globally. Now zoom out to galactic scales. Beyond individual horizons, spacetime curvature still lingers. The gravitational potential around supermassive black holes influences the motion of stars thousands of light years away, but in subtle, cumulative ways. At those distances, cosmic expansion begins to compete with local gravity. The universe's stretching adds another layer of distortion, redshift. Light from TON 618, already bent by the black hole's gravity, is then further stretched by the expansion of the cosmos during its 10 billion-year journey. Separate those two effects. Not easily. Some of the size we assign to TON 618 shadow actually originates from the universe's growth, not the black hole itself. Our tape measure moves while we're trying to use it. These stacked distortions mean that even fundamental quantities like mass blur around the edges. In relativity, Mass is not an intrinsic number but a statement about how spacetime curves around energy. Within a strongly curved region, where energy density shifts and radiation escapes, the boundary defining inside versus outside isn't fixed. The gravitational mass an outsider infers might differ from what an infalling observer would calculate, if they could at all before crossing the horizon. So when we talk about PhoenixA holding perhaps 100 billion solar masses, that figure itself presumes a distant, linear framework, Newton's calm backyard, applied to a domain where straight lines don't exist. Even our tools for visualization betray us. Diagrams that show spacetime as a funnel or grid flatten higher dimensional curvature into something our eyes can handle. They help illustrate conceptually, but they also plant misconceptions, that a black hole sits in space rather than being a modification of space. In truth, the black hole doesn't occupy a location. It is a topology, a rearranged region where metrics loop back on themselves. Calling such an entity large makes as much sense as calling a mathematical equation tall. The descriptor belongs to our limited intuition, not to the physics. When cosmologists simulate the growth of these giants, they often insert them into expanding grids representing cosmic structure. But as those masses increase, their gravitational curvature alters the grid they inhabit. Beyond roughly 50 billion solar masses, simulations struggle because the surrounding space no longer behaves Newtonian enough to stay consistent. The equation approximations break, like a map folded back onto itself. It's numerically unstable, the signature of spacetime protesting against being stretched too far. Even in computers, scale reaches a limit imposed by geometry. Dark matter, too, fudges comparisons. Most black holes sit at galactic centers where unseen halos of dark matter shape the overall gravitational potential. That environment changes orbital velocities we use to infer mass, making two similarly massive cores appear unequal if one sits in a denser halo. Measuring size, without treating the context, is like weighing someone while elevator cables jerk the floor beneath them. The reading tells you more about the elevator than the person. So here's the cliffhanger at the heart of relativity. Everything we think we know about scale depends on reference frames, and near black holes, reference frames disagree about everything. The event horizon isn't a physical shell so much as a boundary in geometry. Depending on who's watching and how they move, its shape and extent differ. What's spherical to one observer may seem flattened or tilted to another moving at relativistic speed. Even the notion of center fades, replaced by coordinate singularities that shift with perspective. That's why physicists sometimes say space and time dissolve at the singularity, not because they vanish in a theatrical explosion, but because the mathematical rules linking one moment or point to another stop providing finite answers. And with that collapse of definition comes the collapse of scale. If nothing can carry a consistent ruler or clock across these gradients, then bigger ceases to exist as an absolute property. The universe's strongest gravitational fields erase the very context that makes comparison possible. Standing back, you start to see the irony. The black holes we rank as colossal are precisely the regions where ranking has no meaning. Their enormity erases the notion of measure. Trying to decide whether Ton 618 or PhoenixA is larger is like debating which end of infinity is higher. Each resides in its own curved pocket of reality where cause and measurement loop together. And that realization pivots us toward a new question, not about size, but about growth. If spacetime bends until metrics lose coherence, how can black holes continue to gain mass? How do these cosmic giants expand within a framework that seems to erase the idea of expansion itself? That's the mystery pulling us forward now. When the universe's rulers and clocks fail, what governs the appetite of the monsters that feed on it? Growth without limits, the feeding frenzy. If everything about scale dissolves near a black hole, that still leaves one burning question. How do these things grow so huge in the first place? Because whatever size means, they clearly accumulate matter on outrageous scales. The physics of that feeding process reveals both how nature sets limits and how certain black holes seem to ignore them. At its core, a black hole grows by stealing orbital energy. Gas, dust, stars, anything wandering too close spirals inward, forming an accretion disk. Friction within that disk turns gravitational potential into heat, and that heat radiates outward. Some fraction of the falling matter gets blown away, but the rest crosses the horizon, adding to the total mass. In principle, you might think growth could continue forever. Just keep feeding the beast and it gets heavier. But cosmic reality enforces a kind of economic rule called the Eddington limit, a balance between gravity pulling matter in and radiation pressure pushing it out. Here's how it works. As gas plunges inward, it heats and shines. Each photon streaming outward exerts a tiny pressure on infalling material. Multiply those photons by astronomical luminosities, and that outward push can stall further accretion. The Eddington limit defines the maximum steady brightness, and therefore the highest constant feeding rate a black hole can sustain without blowing away its own food supply. For a supermassive black hole, that limit still allows growth, but only at a controlled pace. Feed too greedily and the system chokes itself. So how then did Ton 618 bloom to tens of billions of solar masses when the early universe was barely 500 million years old? Even starting from a large seed, growth at the standard Eddington rate wouldn't reach those figures before the epoch we observe its light from. The math demands something faster, and that mismatch has haunted cosmologists for years because telescopes keep finding quasars that seem too massive, too early. One possible answer lies in brief bursts of super-Eddington accretion, episodes where matter floods the disk faster than radiation can escape. Under extreme densities, photons get trapped, carried inward with the flow instead of pushing outward. The disk becomes opaque, more like molten fog than transparent orbiting gas. In those moments, accretion efficiency drops, but the actual mass intake spikes. These phases might last a few million years at a time, long enough to inflate a black hole dramatically before feedback rebalances the system. Computer simulations show that such chaotic feeding could, in principle, produce billion solar mass monsters within the universe's first billion years. Another route bypasses small beginnings entirely: direct collapse. Instead of assembling from stellar remnants, enormous primordial gas clouds in the early cosmos may have skipped star formation altogether, collapsing straight into black holes 100,000 times the mass of the Sun. Give those titans a head start, and the rest follows naturally. Even modest growth afterward could yield the behemoths we see today. Observational hints of such events, dark, compact objects forming where no stars appear, keep theorists intrigued, though the data remain tentative. Mergers add a third mechanism. In dense galactic centers, black holes rarely live alone. Galaxies collide, their central black holes spiral together, and gravitational waves carry away angular momentum until they merge. Each union doubles or triples the mass. Over cosmic time, hundreds of such encounters can stack, particularly in rich clusters like PhoenixA's environment. Those mergers also stir up surrounding gas, triggering new inflow and further feeding, a feedback of growth feeding growth. Yet every proposed path runs into natural breaks. The Eddington limit resists continuous overfeeding. Mergers risk gravitational recoil. After two black holes combine, asymmetric emission of gravitational waves can kick the new one out of its host galaxy entirely, ejecting it from further fuel. And the very energy these giants pour into their environments can starve them. Powerful jets and winds sweep away gas that might one day feed them again. On cosmic scales, black holes regulate their own diets. That self-limiting behavior creates a cosmic paradox. Theory suggests a practical upper boundary around 50 billion solar masses for typical spin rates. Beyond that, radiation pressure and disk instability make sustained growth nearly impossible. But observationally, candidates like PhoenixA flirt with or exceed that threshold. Either the models underestimate what nature allows, or these ultra-sized objects aren't accreting steadily anymore. They might be fossils, relics that gorged in more permissive eras and now sleep off ancient feasts. To see how dramatic this feeding can be, consider the Milky Way's modest central black hole versus an early universe quasar. Sagittarius, a asterisk, adds perhaps a few Earth masses every year in total, mostly from captured gas clouds. A bright quasar feeding at its limit devours several suns per year. Scale that to the inferred rates for the largest quasars, and the numbers climb to hundreds of suns annually during peak activity. The space just outside their horizons becomes a maelstrom of plasma hotter than any core we can reproduce, with particles whipping close to light speed, magnetic fields winding them into jets that shoot across intergalactic distances. Each jet represents energy equivalent to billions of supernovae, all focused into twin beams. Those outflows do more than decorate the black hole, they sculpt galaxies. Radiation pressure carves tunnels in surrounding gas, halting star formation in some regions while igniting it in others. Whole galaxies can transform from blue, star-forming spirals into red, quiescent ellipses because their central black holes grew too vigorously. In that sense, when a black hole feeds, a galaxy evolves. Ton 618 Brilliance once rewrote its entire host's destiny. PhoenixA's gentle but massive outbursts still shape a cluster's thermodynamics today. Growth and environment intertwine so completely that calling the process eating barely captures it. It's cosmic metabolism. And here lies the eerie symmetry. The very feedback that limits local feeding enables larger cosmic structures to stabilize. Jets heat intracluster gas, preventing runaway cooling that would bury the black hole again. It's as if the universe built a thermostat into its own extremes. But temperature and gravity negotiate across scales of billions of light years, not mere kilometers. Each pulse of radiation or jet from a nucleus can take millions of years to ripple through its environment, meaning that the current mass we observe often reflects ancient meals, not recent ones. Even time deceives. The story grows stranger when simulations include rotation. A rapidly spinning black hole converts additional energy from infalling matter through frame dragging, allowing it to emit more power for the same accretion rate. Spin also tightens the inner edge of the disk, where tidal forces are strongest, leading to higher luminosities that may flirt with or exceed the classical limit without blowing everything apart. In effect, spin lets a black hole cheat physics just enough to keep growing. The most massive candidates might owe their excesses not to unlimited feeding, but to near maximal spins maintained through carefully aligned accretion. Then come the cosmic collisions. When two spinning giants merge, their spins can align or cancel, altering how efficiently they can feed afterward. Numerical relativity studies show that a perfectly aligned merger could produce a remnant both more massive and spinning faster than either parent. An energy conversion jackpot. Stack a few such mergers across time, and the composite object approaches theoretical extremes. Humans give them catchy ranks. The universe treats them as statistical outliers of gravitational chaos. But maybe the real magic doesn't lie in any single feeding episode. It lies in persistence. Over 13 billion years, even modest accretion rates compound exponentially. A black hole doubling its mass every 100 million years under favorable conditions can reach billions of suns long before the present. Given enough time and fuel, outright miracles become arithmetic. The boundaries that seem impassable within a scientist's lifetime dissolve across cosmic durations. Still, when we project those curves forward, something uncanny happens. The equations don't forbid endless growth, yet they hint that beyond a certain mass, the definition of black hole itself might fail. As curvature stretches horizons outward, local densities drop, and the event horizon begins to mimic cosmic expansion. The black hole stops being a distinct object and blends into its host's gravitational background, a phase transition from singular entity to spacetime feature. Growth eventually consumes definition, rather than matter. That insight reframes the notion of limitless appetite. The biggest black holes might not explode or evaporate. They could simply cease being recognizable as separate entities. Their horizons merge with surrounding space, diffusing into geometry. In that sense, they still grow, but what grows is the warping of reality itself. Their feeding frenzy transforms from devouring matter to reshaping the metric of the universe. And at that scale, calling anything large or small loses meaning entirely. Black holes expand by bending the very framework that defines expansion. Their hunger derives from geometry's permission to deepen infinitely, while our language clings to finite metaphors. When a black hole bends the growth rules, it isn't just violating astrophysical formulas. It's hinting that spacetime keeps secrets bigger than any quantity we can list. So when you hear that PhoenixA or Ton 618 shatter theoretical limits, picture not monsters breaking cosmic laws, but the universe revealing how flexible those laws become at extremes. Every oversized black hole is a reminder that physics itself is still learning where to draw the line between possible and impossible. Once an object starts feeding on the very rules that define it, growth stops being about matter and starts being about the architecture of the cosmos. And that leads us to the next frontier, the moment when growth collides with the fundamental equations themselves. Because if black holes can bend their feeding limits, the natural question is, can they also break the laws underlying reality? That's where the boundary between physics and paradox begins to blur. When black holes break physics, there's a point in every black hole discussion where the math stops cooperating. Up to now, gravity has been the storyteller, warping space, slowing time, stretching light. But at the very core of a black hole, gravity's script collides with itself and the plot breaks down. We call that place a singularity, yet even that word is an admission of defeat. It's the mathematical equivalent of error, undefined. In theory, a singularity is where density and curvature become infinite, a single point where the entire concept of distance no longer applies. According to general relativity, once matter crosses the event horizon, it collapses inexorably toward that center, squeezing everything into zero volume. But zero volume and infinite density aren't just extreme numbers. They're warnings that our equations are missing something vital. Nature doesn't build infinities. Humans do when our models crack. This is where general relativity, our best description of gravity, encounters its nemesis, quantum mechanics, our best description of everything else. Relativity treats space and time as smooth fabric. Quantum theory sees the world as granular, governed by probabilities and uncertainty. Near a singularity, those views can't both be true. The curvature predicted by relativity grows so extreme that quantum effects should matter, but our equations can't yet blend them into a single story. The place where they collide is where physics, as we know it, breaks. Think of the singularity not as a tangible point, but as a region where our measurement concepts collapse. Inside the horizon, all paths, even lights, curve inward. Information about what happens there never escapes. That means no experiment can confirm what reality looks like beyond that threshold. For all we know, the infinite density might soften into something quantum and finite. Perhaps matter forms exotic states or space itself dissolves into a Planck-scale froth. We simply lack the physics to describe it. Yet incompleteness hasn't stopped us from probing with mathematics. Quantum gravity proposals, like string theory and loop quantum gravity, try to stitch both worlds together. Some suggest that singularities don't truly exist. Instead, they're replaced by tiny cores where spacetime's granular nature repels further collapse, a kind of quantum bounce. Others imagine that whatever falls past the horizon eventually tunnels into another region of spacetime, forming a white hole or even spawning a new universe. Those ideas remain speculative, but they share a message. Our current laws are provisional. The biggest black holes aren't just astronomical bodies, they're laboratories testing the boundaries of physics itself. To see why, picture two ultramassive black holes, each tens of billions of solar masses, drifting toward one another in a galaxy cluster. As they spiral closer, they radiate gravitational waves, ripples in spacetime itself. Those waves carry away angular momentum, drawing the giants together until their horizons touch. Here, something strange happens. Instead of two surfaces merging like soap bubbles, relativity predicts they fuse seamlessly into a single larger horizon. The instant of collision erases all distinguishing features. Mass, spin, charge. These parameters redistribute, and everything else disappears behind the new unified boundary. From outside, that process obeys energy conservation perfectly. The total mass after the merger equals the sum of the inputs minus the gravitational wave energy radiated away. But peek at the simulations near the merged core, and the story bends. The curvature spikes so high that current numerical methods blur. Coordinate grids tangle like cloth pulled too tight. Even our best supercomputers hit computational singularities of their own. In a literal sense, we can't finish the math describing the universe's most violent, simple collision. That blindness leads to an uncomfortable question. If two black holes merge into one continuous horizon, where do their internal singularities go? Are they destroyed, or do they coexist inside separate pockets disconnected from our spacetime? Relativity doesn't specify. Some theorists argue that the interior becomes a single extended distortion, no longer a point, but an entire region where the laws of nature rewrite themselves. Others suspect information about each original singularity survives as subtle quantum patterns on the new horizon's surface, encoded in faint correlations of Hawking radiation. Ah yes, Hawking radiation. Stephen Hawking's 1974 breakthrough showed that black holes aren't perfectly black. Quantum fluctuations at the event horizon allow pairs of virtual particles to appear. One falls in, the other escapes. Over immense timescales, those tiny leakages cause the black hole to lose mass, evaporating eventually. But that idea reignited another paradox. If radiation carries away energy, yet seems to contain no trace of the information that fell in, does the universe destroy information? Quantum mechanics insists it cannot. Relativity doesn't seem to care. Trying to reconcile their disagreement is like teaching two languages to converse without a dictionary. For small black holes, this debate centers on subatomic detail. For monsters like Ton 618 or PhoenixA, it scales into absurdity. Their evaporation times exceed the current age of the universe by factors of trillions upon trillions. Any quantum effect is effectively frozen, but the principle still matters. Even infinite mass doesn't excuse inconsistency. Somewhere between the classical horizon and the quantum foam, beyond it, lies the answer to how reality prevents contradictions. One hint comes from attempts to calculate maximum entropy. According to thermodynamics, every system contains a finite amount of information corresponding to its microstates. Jacob Bekenstein discovered that a black hole's entropy scales with the area of its event horizon, not its volume. The larger the horizon, the more information it can encode. This strange law, now a cornerstone of black hole thermodynamics, suggests that the interior complexity of a black hole is somehow projected onto its surface. In that holographic picture, inside and outside exchange meanings. A black hole's fundamental data live not in its depths but on its boundary. That insight leads to a radical idea often called the holographic principle. The universe itself may function like a black hole on a cosmic scale, with all its information encoded on a distant surface, the cosmological horizon created by expansion. If true, our reality could be the three-dimensional projection of two-dimensional information woven into the fabric of spacetime. Black holes, then, aren't exceptions to the universe. They're its most literal expressions. Their rule-breaking behavior hints that the entire cosmos shares their logic. Now return to those limits we set for mass, 50, 60, 100 billion suns. Those numbers arise from the point where radiation pressure, spin, and accretion physics balance gravitational pull. But tune those variables toward the extreme, a nearly maximal spin configuration, perfectly aligned feeding disks, and the viable mass limit stretches further. Extrapolate far enough and you reach absurdities. Black holes large enough to encompass galaxies, or, in theory, the observable universe itself. At that point, largest turns meaningless. Anything that big would curve space so completely that it wouldn't sit in the cosmos. It would be the cosmos. Physicists don't claim such ultimate giants exist, yet the math doesn't forbid them. The equations merely stop giving interpretable answers once horizons overlap cosmic boundaries. Insert inflationary models. Pockets of spacetime could pinch off into baby universes with reality structures identical to those near singularities. Some researchers even argue our own universe might be the interior of a black hole formed in another. It sounds speculative, and it is, but the thread of reasoning is consistent. Whenever mass, energy, and curvature reach extremes, relativity stops distinguishing between black hole and cosmos. They become geometrically equivalent solutions of the same field equations. That symmetry reframes the question we began with. We asked which black hole is biggest, measuring in solar masses and kilometers. But if black holes and universes exist on the same mathematical continuum, biggest no longer applies. There is only curvature, varying by degree, reshaping the coordinates within which we draw comparisons. The labels we cling to, mass, radius, boundary, are conveniences that crumble when stretched past limits. When a black hole breaks physics, it doesn't explode or vanish. It reveals that our framework was partial all along. The theories that ruled ordinary space falter under their own weight, not because reality changed, but because we reached the horizon of understanding. TON 618 and PhoenixA hint at that boundary, one through blinding light, the other through silence heavier than matter. Both whisper the same secret, that scale and law are local phenomena, valid only until gravity folds them. And this is the paradox at the heart of every record-breaking discovery. The further we chase the largest, the more the concept itself dissolves. The universe invites us to measure the immeasurable, then changes the ruler mid-experiment. These black holes don't just warp spacetime. They expose that physics is a scaffolding we've built on assumptions of scale, assumptions that fail where gravity becomes absolute. What replaces those assumptions? Maybe a future theory that unites quantum uncertainty with cosmic geometry. Maybe new observations revealing how information escapes horizons. Or maybe the answer lies in accepting that some questions have no static solution, that reality, at its deepest, resists final form. For now, when asked which black hole is the biggest, the honest response might be none, because each one expands into a region where bigger no longer exists, and where the universe, through them, remembers that even its own laws are temporary sketches drawn on an infinite canvas still unfolding. The scale illusion, why we can't compare them. After everything we've seen, the warped horizons, the uncertain masses, the feedback loops, it's only natural to wonder why we still keep comparing them. But here's the catch. Every comparison we make between black holes happens across different realities. Not metaphorical ones, literal ones, epochs separated by billions of years, frames of reference diverging because of relativity and expansion. So when we talk about TON 618 or PhoenixA as if they're rivals, we're trying to rate shadows cast on different walls of the universe. Each supposed largest black hole comes from data frozen in time. TON 618 light began traveling toward us more than 10 billion years ago, meaning we're watching it as it was when the universe was young and dense, before many of today's galaxies even formed. PhoenixA's signal left 5 to 6 billion years ago, when the cosmos had already slowed its growth and galaxy clusters were mature. They don't exist for us simultaneously in any meaningful sense. To compare their sizes is to compare two photographs taken billions of years apart, and pretend they're snapshots from the same moment. That temporal dislocation stems from look-back time, a direct consequence of the finite speed of light. The farther an object lies, the older the light we receive. So the ton 618 we measure is effectively a fossil. By now, it could have merged, changed, or even gone dormant. PhoenixA, seen in relative middle age, reflects a different stage of cosmic evolution. When you place their records side by side and rank them, you're not comparing like for like. You're stacking two slices of history drawn from incompatible eras. Add to that cosmic redshift, light stretching across expanding space shifts toward longer wavelengths, warping not only color but also brightness. That distortion folds directly into how we estimate distance and mass. Increase the redshift slightly, and the inferred luminosity inflates, boosting the calculated size. Correct it differently, and the same data shrink. Cosmic expansion acts like a zoom lens that refuses to hold focus. When astronomers claim a black hole weighs 60 billion suns or 100 billion, those numbers hide systematic uncertainties born from a universe that won't sit still. The distortion doesn't stop there. Light from quasars often passes through intervening galaxies on its way to us, a process known as gravitational lensing. The gravity of those midway systems bends and magnifies the incoming light, like uneven glass distorting a distant candle. For ton 618, we can't fully rule out subtle lensing effects that might exaggerate its brightness. A slightly magnified quasar looks brighter, suggesting a higher accretion rate, and by inference, a heavier black hole. Even a few percent of lensing enhancement could boost the mass estimate by billions of solar masses, enough to upset any leaderboard. PhoenixA, observed mainly through X-rays rather than optical light, suffers less from that specific bias, but carries its own modeling uncertainties. Comparing the two becomes an exercise in error propagation. All those layered distortions reveal a deeper point. Our entire measurement system assumes linear cause and effect, yet cosmology plays in non-linear rules. When distances stretch, timescales warp, and radiation loses energy on the way, additive comparisons fail. Think of it like comparing two mountains viewed through funhouse mirrors bent in different directions. You can describe each reflection precisely, but lining them up becomes meaningless. Astronomers know this, of course. In scholarly circles, they rarely declare an absolute largest black hole. Instead, they categorize by redshift range or method of inference, careful to note that each candidate's apparent mass emerges from its own calculation pathway. The oversimplified hierarchies, the ones that seep into press releases, are distortions introduced during translation from technical literature to public excitement. We love the narrative of beating records, but the universe loves subtler truths. This tension mirrors the difference between precision and accuracy. We can measure spectral lines of ton 618 to remarkable precision, down to fractional nanometers, yet those precise numbers feed into models full of assumptions about geometry and orientation. The digits behind the mass estimate may look certain, but the underlying reality is elastic. For PhoenixA, the uncertainties are explicit. Models depending on energy budget balance differ by factors of several. So both extremes of uncertainty lead to the same paradox. Accuracy evaporates exactly where our precision soars. The other illusion hiding here is simultaneity. Because cosmic expansion drags space itself apart, distant regions recede faster than the speed of light relative to us. That doesn't violate physics, it's space growing, not objects moving through it. But it means there's no global now. We observe each black hole frozen in its private timeline. Comparing them assumes a shared cosmic moment that simply doesn't exist. Which one is bigger right now? Is meaningless. The universe never synchronizes its clocks. Even scale models we see, the visual comparisons showing black holes lined up beside planets or galaxies, reinforce the misunderstanding. They convey size as though all were placed on the same cosmic floor. In reality, each sits within its own curvature and epoch, translated through layers of interpretation. Those diagrams simplify scale for intuition, but they also anchor illusions. It's not that scientists lie. It's that our brains need pictures to make sense of invisible geometry, even when the pictures distort truth. Let's dig deeper into how expansion warps comparison. Imagine cosmological standard candles, objects whose intrinsic brightness we think we know, supernovae, quasars, certain variable stars. Using their apparent brightness, we infer distance. The reliability of that distance, in turn, shapes our measurement of a black hole's mass once luminosity enters the equation. But the farther we peer, the more dark energy inflates space and shifts those calibrations. A small error in cosmic distance ladder estimates ripples upward into giant uncertainties in black hole masses. Our cosmic ruler isn't just curved, it's stretchable. That's why astrophysicists increasingly refer to mass functions instead of superlatives. A mass function describes populations by probability distribution. It's an admission that individual comparison makes little sense. Statistically, yes, we can talk about ultramassive black holes as exceeding 10 billion solar masses, but within that category, trying to crown a single champion ignores overlapping error ranges. Most of those massive objects likely inhabit different gravitational contexts anyway, quasar environments versus cluster cores, each altering emissions in unique ways. The moment you compare across contexts, science blurs into metaphor. And yet, this realization doesn't drain wonder, it deepens it. It means that every measurement we make is intertwined with the architecture of the cosmos itself. The error bars on ton 618 mass aren't imperfections. They're signatures of the universe's evolving geometry stamped onto our data. Each uncertainty tells us something about how space has stretched, how time has flowed, how energy has been processed along the light's path. Our difficulty comparing them is exactly what proves relativity true on the grandest scale. There's also a hidden psychological layer. Humans crave linearity, bigger, smaller, faster, slower. It's how we evaluate meaning and progress. But in a cosmos governed by curved geometry, linear thinking fails. The hierarchy we keep imposing, ranking giants that no longer share a common frame, reflects our need for structure, not nature's. When we finally accept that, the topic transforms from competition to revelation. Instead of asking which is largest, we start asking, what does it mean that we can't compare them at all? So here's the mind twister. The black holes we label as largest expose not their dominance but our dependence on reference. They remind us that measurement is a conversation between observer and universe, not a decree about objective reality. The scale illusion isn't an error in data, it's a misunderstanding of perspective. We can trace light curves, compute masses, and still miss the essential truth, that every number we assign carries the fingerprint of our own cosmic location. And perhaps that's the real takeaway. When science matures enough to map uncertainty onto meaning, we realize that the impossibility of comparison is itself the lesson. Ton 618 and PhoenixA aren't rivals. They're different dialects in the universe's language of gravity. One speaks in ultraviolet brilliance, the other in X-ray quietude. Trying to rank them is like deciding which language is louder. The beauty lies in translation, not competition. So the next time a headline declares a new biggest black hole, remember, that record holds only within the thin bubble of assumptions we occupy. Stretch the bubble, shift epoch, observer, geometry, and the record dissolves. The universe hasn't lied, our categories have. Biggest turns out not to be a fact but a perspective, a temporary mirage created where measurement meets relativity. And once you see that mirage for what it is, the horizon widens. The question evolves from which is largest to what else lies beyond the scales we can compare. That new curiosity, freed from scoreboard thinking, is the bridge to the next idea. Maybe the term big itself needs redefinition. Because if scale depends on context, maybe greatness in the cosmos isn't about dimension at all, but about transformation. And that perspective shift, that turning of measurement into meaning, is exactly where the story heads next. Rethinking what big means. So after all this, after the measurements, the paradoxes, the illusions, the question that started everything comes full circle. If biggest can't survive physics, what does big actually mean? Because the answer isn't in kilometers or solar masses. It's hiding in the way these black holes reshape the universe and quietly our understanding of it. Through TON 618 and PhoenixA, we've learned that size no longer belongs to objects. It belongs to influence. A black hole doesn't just occupy space, it rewrites its environment's rules. It bends light paths, disrupts star formation, sculpts galaxy clusters, even participates in cosmic feedback that regulates heat across millions of light years. When a single gravitational well can steer the fate of hundreds of galaxies, calling it big feels inadequate. These aren't bodies to be measured, they're mechanisms of transformation. Think about that shift in meaning. In everyday life, size implies boundaries. Something has edges defining where it stops. But with black holes, edges vanish. Their presence defines where observation ends, where information itself falls silent. PhoenixA's jets contain more energy than all the stars in the Milky Way, released invisibly into a medium we can only trace through X-rays. TON 618 glare outshines entire clusters, yet reveals nothing about what lies inside. In both cases, largeness isn't an extension outward, it's an intensity inward. Greatness measured not by volume but by effect. That thought reframes everything. The largest black holes aren't monuments, they're processes, cosmic negotiations between gravity, matter, and time. They rebuild their surroundings until galaxies reorient around them. The same gravitational field that swallows light also seeds structure, stirring turbulence that triggers or halts new suns. Big isn't a number, it's a kind of authorship, the capacity to rewrite cosmic narrative. This shift mirrors a deeper pattern in science. Each time we chase the extremities of measurement, the object we think we're studying disappears into relationship. In atomic physics, matter becomes probability. In cosmology, distance becomes curved time. Now with black holes, size becomes transformation. The theme is constant. The further we push definition, the more the universe answers with verbs instead of nouns. TON 618 isn't large. It's doing largeness. It enacts curvature and causality on the grandest scale imaginable. There's humility in that realization. The human instinct to classify, to rank, label, set records, turns out to be too flat for a curved cosmos. We crave scale because it comforts us with order, but the universe expresses itself through patterns of interaction, not hierarchies of magnitude. The real hierarchy is one of influence, which systems change the most realities around them. By that metric, a smaller black hole that seeds an entire galaxy's evolution could be larger in significance than a quasar that merely glows. Maybe bigness should mean something closer to reach, the span of consequence. PhoenixA, in its silence, reaches into the thermal history of a whole galaxy cluster, dictating how hundreds of trillions of stars will or will not form. TON 618, though farther away, tells us what physics allowed matter to organize so quickly after the Big Bang. They're boundary stones in time as much as in space. To call either biggest is to compare amplitudes in a song that never plays the same note twice. Still, this redefinition doesn't kill wonder, it amplifies it. Because once you let go of linear comparison, the cosmos opens from competition into continuum. Big becomes a question about cooperation between forces, gravity guiding light, entropy feeding order. Every black hole, massive or modest, participates in that loop. They connect stellar death to cosmic architecture, turning collapse into creation. That paradox, that something defined by disappearance becomes the engine of structure, is the most astonishing scaling law of all. And maybe that's why we keep peering back into the dark despite every warning that our numbers break there. Deep down, we sense that black holes aren't merely destinations of matter, but reflections of understanding itself. They represent the point where curiosity crosses its own horizon. We fall toward what we can't see, pulled by need to know. To grasp them even partially is to glimpse how reality folds meaning into mechanics. Imagine explaining this to the first astronomers who cataloged the sky by brightness alone. They thought bigger stars meant more perfection. Then telescopes grew stronger, and bigger became relative to distance, not divinity. Now our instruments stare into places where scale itself disintegrates, and suddenly bigger returns as philosophy, a measure of perspective rather than substance. Every discovery of an ultramassive black hole doesn't just extend astrophysics, it stretches language. So what does big mean now? It means system-wide consequence. It means power to alter entropy flow, to shape the geometry that defines other things' motion. It means rewriting laws locally so completely that our rulers fail. In that sense, the biggest black hole is always the one that challenges our definitions the most, the one that forces physics to evolve. The moment theory can comfortably hold one of these monsters, the universe introduces the next anomaly, as if to remind us that meaning, like matter, has horizons yet to cross. There's poetry in that uncertainty. When we call a black hole big, we're really describing our smallness beside the scale of transformation they represent. They teach proportion through paradox. Just as Ton 618 shows light trapped by its own brilliance, and PhoenixA shows silence heavier than stars, both reveal that true magnitude lives in contradiction. The more absolute the darkness, the more infinite the insight it offers. In the end, maybe the biggest black hole isn't out there at all. Maybe it's the conceptual gravity pulling our minds toward the limits of comprehension. The cosmos lets us chase measurements so vast they collapse our instruments and still whisper that we've only begun. If size measures reach, then curiosity itself may be the universe's largest phenomenon, the one horizon that keeps expanding no matter how much we learn. And that's the takeaway worth remembering. Big isn't a property, it's a perspective, the space between what we can explain and what still overwhelms explanation. Black holes embody that space perfectly. Each one is a silent reminder that the universe grows not just by stretching matter, but by stretching thought. They don't just swallow light, they illuminate how infinite understanding can become when we finally stop trying to rank infinity. The mind-bending takeaway. So after chasing records across 10 billion years of light and bending mathematics until it snapped, what's left? The realization that calling any black hole the biggest misses the point entirely. Because a black hole doesn't just occupy a location in the universe, it bends the space that defines what location even means. Its gravity reshapes the ruler we try to use against it. The more massive it grows, the more language itself collapses around the attempt to describe it. Here's the mind bender. Black holes don't exist inside the universe the way planets and stars do. They're conditions of spacetime, folds in the cosmic fabric so deep that inside and outside trade places. To say one is largest is like saying one infinity outruns another. Ton 618, PhoenixA, or some unseen titan beyond our telescopes. They're not contestants. They're boundaries where causality folds back on itself, where our definition of measurement evaporates into curvature. Think of what that means. When we rank these cosmic monsters, we're measuring the edges of understanding, not the edges of matter. Each discovery extends the horizon of what the universe allows us to know. So in the end, there's no single champion, only the idea itself, the unstoppable gravity of curiosity pulling us toward new limits. That's the real viral force in science. Not what we know, but what we can't stop wanting to know. The deeper we stare into the dark, the more the universe dares us to keep looking. If there's one truth to keep, it's this. Black holes aren't objects growing in the universe. They're places where the universe grows inward, exploring its own capacity for transformation. The biggest black hole is never a number, it's a question. And if you're ready to keep falling toward the next one, subscribe and join us as we explore how reality itself bends under cosmic law.